Ladies and gentlemen, please join me in welcoming Matt Mahvi, owner and CEO of Staminus Communications.
I'm Matt Mahvi with Staminus Communications. Good morning, everybody. It's my first time in Iceland. Very excited. Beautiful place. So none of these pictures I have the copyright rights for, so Mr. FBI, please don't take me into custody. I apologize in advance. The world is a wonderful place, but it's full of dangerous things. It's very scary out there, as we just heard for a while. It was a great presentation. This is what we do. We just, combat it and fight it. Bring it on, baby. And then we make it a lot better. There was a bunny in this picture, but he died. It was collateral damage. The Jaeger bot just took him out. It was very sad. So, any questions? That's the end of the presentation. Yeah? Q&A? No? Okay, well, just kidding. It's very small, but it says JK smiley face. So this is what we do. We protect against distributed denial of service attacks. Does anybody know what DDoS is? Anybody? Raise hands, show of hands? Oh, this is a lot more than most of the time. Awesome. So DDoS is a problem. Imagine a highway that's just completely packed and someone can actually initiate that by choice. It sucks. Because then commerce stops, interstate commerce stops, everything stops across the world. I mean, you can't access Facebook, results in global depression. I mean, everybody gets really sad, and then you got to sell a lot of Prozac. According to Forrester, if you have a significant presence on the internet, you're going to get attacked. It's just natural. It's really a matter of when, not a matter of if. If you generate a sufficient amount of revenue online, you're going to get attacked. It's just natural. So this is really interesting. This is from Emerson Power. Emerson Power generates and produces electrical equipment for distribution in data centers. An outage can cost up to $7,900 per minute. That's insane. And that varies across different data centers and different kinds of industries. But the number 2 cause is cybercrime, and we just heard. That's crazy. That's a lot of damage per minute of outage. And an attack can last minutes, hours, days, weeks. So how much would an attack cost you guys? I mean, if you really think about it, if you're producing like $1 million a day in sales, which for a large company is not that significant, right? I mean, $1 million, Amazon produces significantly more than that. They're out for 1 minute, 5 minutes. I mean, imagine when you guys go to a website and you try to order something and xyz.com is down, what do? You hit your browser back button, you go to the second search, and then you order from somebody else because it was down. You don't want to wait. Nobody wants to wait. So with PayPal, for example, a few years ago, they had sporadic outages for about a week of sporadic, not downtime, just sporadic up and down. They lost over $5 million, just like that. It was just evaporated money, gone. And how much does it cost to protect against these things? Sometimes it can cost millions of dollars in equipment, bandwidth, staff. It gets very expensive to start protecting against these things. And just regular routers, even though they have that checkbox that says protect against DDoS, doesn't actually really work and protect against the large-scale attacks. It gets a little bit more complicated than that. So the solution is really insurance. That's where it's at. Everybody has got graphs, right? And everybody's graphs always go up, so we've got the graphs that go up as well. But the general gist of it is attacks are always on the rise. And our friend in the previous presentation pointed out the Internet of Things. The Internet of Things is great because every device on the internet is going to get, every device in the world is going to get an IP address. IPv6 is 128 bits. That's so many IPs. Everything is going to have an IP address. And if you think about it, not all of these systems are going to be protected and secured. So they're going to get hacked, and they're going to be used in large-scale botnets to launch enormous DDoS attacks. We're just at the beginning. We just recently saw between November 2013 and February 2014 NTP amplification attacks. NTP is network time protocol. Very simple. It's what your phones use to synchronize time generally, or what your computer uses to synchronize time. And the NTP amplification attacks were essentially these massive cannons that would take down entire countries of internet. So the attacks would range over 400 gigabits a second. I'm talking about an enormous attack. Like entire cities in the United States would go offline. NTT North America in Los Angeles had a 6-hour outage because of an NTP denial of service attack. These things were incredible. During Pacific Telecom Council, which is a council in Hawaii every year for all the ISPs pretty much in the United States and Southeast Asia, they were called the transit killer. And denial of service attacks happen for a lot of reasons. Political protest, business sabotage, disgruntled employees, which we have none here, none at all, no disgruntled employees here, infamy and extortion. And I mean, you would imagine that it's going to be very complicated to launch a denial of service attack, but it's really not. It can cost less than $5, and it's very easy. You can even launch them from your phone. Please don't do that right now against anybody. And it's crazy. It happens to every industry. I mean, there's so many news articles all around where denial of service attacks happen. Like Sony recently, right? EVE Online, that's a company that in Iceland that produces EVE Online. They were just impacted by denial of service attacks. Video games all across the world, news agencies, government agencies. GitHub got attacked. We actually protect a lot of charity websites for free, and charity websites get attacked. I remember a few years ago, we had a company that did research on rare cancers. It was rarecancer.org, and they sustained a denial of service attack. That was just crazy to me. We have a children's hospital. It's a charity children's hospital, and they get attacked. It makes no sense. There's so many reasons why people get attacked. I mean, you figure it's just financials and stuff like that, but no, it's not just financials. It's not just retail websites. It happens to everybody, and it's across the board. Voice over IP, airlines. I mean, you just name it, and they get attacked. There's so many reasons why people want to attack. So this is a great example of an attack. Can anybody at all identify it? I'd like you to please raise your hand and point out where the attack is. I've had a hard time figuring this out myself. I can't figure it out. So this attack came in a little while ago. This is actually one of the smaller attacks we've sustained. Mid-size, I want to say, not smaller. This would have taken down all of Iceland. This is 140 gigabits per second and 80 million packets per second. And it's not just Iceland. This would have taken down virtually every network in the world, not in the top, like, 20, because it's so gargantuous. Nobody really has 140 gigs of transport capacity across the world to be able to carry that kind of traffic. I mean, you're talking about transatlantics not having really that much overhead available, no real cities, no real networks. 80 million packets per second. How many of you guys run like IIS on your web servers? IIS? Okay, so this is 80 million packets per second. IIS on the internet is probably going to be able to sustain maybe between 50 and 100 packets per second. It's an order of magnitude higher. Apache maybe 200 to 300, 500, depending on how you tune it. Nginx, maybe a few thousand, 5,000 packets per second. If you throw a varnish in front of that, you might hit like maybe 50,000 packets per second. You throw up an F5, you're going to hit some pretty good performance. You're still not going to hit 80 million new connections a second, which is pretty intense. So this attack can pretty much take down any website on the internet except for maybe Google or Amazon or really any of the top 20 websites who already have something in place or anybody who already has denial of service mitigation in place. These things are enormous, and they come in an instant. It doesn't ramp up, as you can see. It's just boom, you now have traffic, and you don't know what to do with it. And it's really easy to launch one. So if you go Google top 10 booters, it's going to be really funny. There's actually a website that's top 10 booters, and you can order it online. They have support services. They have ticket help desks. You pay this one's on sale, actually. It's $2.50. And they're called stress testers. So, I swear, officer, I was just stress testing that website. But really don't do this, please, seriously. I know I'm showing you stuff, and yeah, don't do it. It's really simple, though. You don't actually need to hack a big old botnet. Somebody's already done that for you on all the hard work. They've released the worm to expand and go take over the world, and now you have this incredible cannon at your disposal. And it didn't take very much background checking. It just took a credit card or Bitcoin. So we've been doing this for a while. We protect thousands of companies, millions of users, billions of visits. It's actually not every year, billions of visits every month. That's wrong. We've been doing this for a long time. So it's a fun project. We've done it under different names. Our first attack was somewhere around November 1998. He was a disgruntled customer. That's when we learned the hard way not to piss customers off. And then we had to figure it out. There was nothing at the time to stop it. We had to figure it out. We made modifications to the Linux kernel, started adding features in, and the rest is history. So we're all around the world right now. We're distributed globally. That's the only way to really stop attacks. You can't stop it in one city. It's not possible. The magnitude of attacks is such that you will take down that city if you try to stop it in just one city. You'll take down transatlantics. You'll take out various transport circuits. So about 2 years ago, we were contracted with an ISP. I can't tell you their name, but I can tell you privately later, over a couple of drinks potentially. So we actually got attacked, and we took down their global backbone twice over Saturdays, one Saturday and then another. They impacted probably hundreds of millions of people all around the world, and there was significant impact because of the impact that was caused by our denial of service attack against us. Their network just couldn't sustain it. This is a little bit more technical. I'm not going to get too deep into this. I really just put this up in case somebody downloads it and wants a little bit more information. The general gist of it is it's fully automated. Everything is deep packet inspected. We look at every packet. It's not flow-based. Everything has to be inspected because you can't do flow analysis. If you guys are familiar with S-flow and NetFlow, it's a sampling mechanism. You don't really get a lot of data. In order to stop slow attacks, complex attacks, we have to generate signatures and heuristics against these attacks with deep analysis of the data, and it's fully automated because you can't have somebody sitting around trying to fight attacks. We're not firefighters. What we are is software developers. This is my favorite picture. Let's get technical. I mean, this guy is Felix the cat. He's very smart, very scientific. So this is a portion of the presentation where anybody wants to check their emails, get their Facebook out, feel free. It's going to get a little bit technical, not too technical. I won't get offended, I promise. So the core challenges with denial of service mitigation for us were these, and I'll start to get through them, but this is why we had to develop our own solution. A6 versus x86. This has been a debate for a long time, and x86 is really starting to take a lot of traction. With the recent E5 V3s, we have 18 cores per processor, and x86 has the fastest development cycle out of any processor. So they're going to generate the most bang for your buck in terms of performance. They're also really, really inexpensive and easy to program for. So when you buy an Intel, for example, they always come with this awesome handbook that tells you how to program for the Intel. And if you actually program to the specifications of the processor, it's an amazing, amazing processor. As long as you factor in things like cache coherency and memory bottlenecks, so you're not breaking the processor internally because of the massive number of cores. This is how we're able to achieve the performance we're able to achieve. The next one is routers and not as firewalls. Everybody's here got a router, right? You guys got your 6500s with your Sup 723BXLs, right? Your MX routers, your new ASR 9Ks that you just got approval for. Those are pretty awesome. They all have little firewalls inside, features that you can throw up ACLs and stuff. Well, you're not really supposed to throw up a lot of them, especially not over 100,000, over 1 million, or over 1 billion. And if you start putting stuff into those and taking them out really, really fast, like, for example, with FlowSpec, things behave a little oddly. And by oddly, I mean they crash. And when your router crashes, it's not a good day. I mean, you guys are laughing over there because you've probably done it, right? Your router starts to crash. And if anybody's ever had that weird router crash where your data plane is now disconnected from the front end and you don't know why it's behaving the way it's behaving, probably because you started messing with it too much. It's best to leave routers to do what they're designed to do, which is to route. Our firewalls are firewalls. We can run 14 million packets per second, which is almost line rate, pretty much line rate with some overhead. It's 6 cores. And we can do 2 to the 32 static blocking and whitelisting. I mean, that's pretty awesome. Thousands of static signature blocks, and it's all because of dynamic reoptimization that we can implement. Hash performance. I know marijuana is illegal here, but I thought I'd throw up the little hash. It's smoking fast, right? Like puff, puff. Just kidding. I don't do that. So you might be able to see some of the processor stuff there, but we have different kinds of hashes for different kinds of memory allocations, and that's part of why we get the magic that we do. It's because we've worked so extensively on making sure our collision rates are low. I mean, that's at the end of the day the point of a hash, right? You got to have a smaller amount of memory than what you actually need, and then you have to reorganize it dynamically, garbage collections and so forth. Ring performance is also really important. I mean, my precious golem. So this is really, really important as well. With rings, the concept is that you have like a single producer, single consumer, multi-producer, multi-consumer. So as long as you're not blocking, and you guys, a lot of you guys probably know, I mean, when you start to block and you do spin locks and stuff like that, you're really causing a lot of problems, especially if you're doing like p-thread context switches. We can't do those. You can't go into the kernel, out of the kernel. We have to be outside of the kernel the whole time or inside the kernel the whole time. You can't really keep context switching. So in one core, our consumer producer runs 18 million per second. 18 million in one core. That's a synthetic test. It's not real world, because in real world there's a lot of other stuff that happens. But it's pretty awesome. Things like packet queuing and dequeuing, transmission stack processing, and BGP kickbacks are what we use the rings for. It's just really efficient for managing packet distribution. And horizontal scaling is really important because we can buy one big box with the biggest, baddest processors we have, right? Like super bad processor, awesome. But at the end of the day, one box is one box. That's it. We have to figure out how to scale it up horizontally. We've got to throw up more boxes. So we figured that out. LACP is great for this. The problem is LACP isn't always consistent. You always have outliers. So you're not hitting the same box every time with the packets, even though hashing algorithms should theoretically do it. But what happens if you take one box out of the hash, out of the LSCP hash? Now you have a redistribution and packets go all over the place. Well, if we didn't solve this, our horizontal scaling would result in false positives. And that's what we can have. So we fixed this with IAS, Intelligence Acquisition System. The concept around this is that our boxes dynamically talk to each other. And that way we don't have to have any single box with the complete space of all our state tables. One box will have some subset of the state table overlapping with other boxes. Think of it almost like in a RAID fashion. And this resulted in us allowing us to do blade distribution. So what happens is now we throw blades and blades and blades and blades, and that's how we get the performance we need to get out of our processing. And imagine this. Now we have a blade of a particular generic processing for data packets and so forth, and we can kick back to another blade of very specific processors. For example, GPUs to do our Bloom filters for large-scale dictionary matching. So things like that really end up awesome because now we have very specific processing for specific types of tasks in deep packet inspection. And DPI scaling is where it's at. This is where it gets really complicated because you guys have all used Snort, right? Like who's used Snort before? Snort is great, right? Snort is awesome. It's really cool. It's really CPU intensive though. So as long as we can do DPI really efficiently, we can maintain our performance. And at the end of the day, what we are is an IDPS that focuses on high performance analysis blocking. That's what we really are. We're not focused on slow, we're focused on fast, whereas Snort is focused mostly on just like large scale complex rules and so forth. And dynamic reallocation and reorganization of our rules is really where it's at, and efficient matching on packet inspection and string matching. Like we're not doing complex string matching that's super slow because we can't. If we do, we start breaking away from performance and then our customers aren't very happy about that. So what do we protect against? Everything. We have to. You can't just protect against some stuff, right? The only thing we don't protect against is the scissors. So if someone comes in and cuts your line, I'm sorry, but we can't protect against that attack. That's the only one we really don't focus on. Everything else is really is fair game for us. Slow attacks are really fun, especially because you got just a few requests a second coming in. And if your website, for example, has the problem of like 1,000 SQL queries on index.php, that might pose a little bit of a challenge for us, so in that case, we throw up a caching engine in front. But for the most part, everything works around our mitigation directly, again, with the back-end customer. We have pretty graphs as well. That's all I can say about pretty graphs. I mean, we break down the traffic, and they're very colorful. It's jQuery stuff. Advania. We've been working with Advania for a year now. We've been integrating into their network. Working very closely with their senior network engineers and their overall integration team. It's been a blast. Really love working with them. They have exclusivity in our services in Iceland. The service is redundantly secured. There's a couple of challenges with delivering to Iceland which were unique for us, and we weren't actually able to deliver to Iceland directly. The primary challenge with delivering to Iceland is that we normally deliver our services over a generic route encapsulation tunnel. It's a GRE tunnel. And when we deliver over a tunnel, we have to deliver over transit services. Well, Iceland doesn't have hundreds of gigabits of transit capacity. So if we were to deliver our security over that, people would simply attack the transit endpoints and take down the country's transit, bringing our service down. We wouldn't be able to deliver the security. That's a challenge. So what Advania did was allocated transport circuits out of the country specifically for the delivery of this service, which is phenomenal. It was amazing. That actually solves the problem. Service is deep within Advania's network and allows for quick turn-up. This is, and please don't read this as well, but this is roughly an explanation of how things are designed to work with the Staminus appliance. We have an on-premise appliance as well as cloud mitigation services. But things can be always on or on demand either way, and it's fully automated. That's kind of the magic around it. Deployment is with anybody's IPs. We anycast it and we throw it up, or they can be Advania's IPs or load balancers. We have load balancers in front to protect against those IIS problems and Apache problems. So you guys can contact Advania for any information. Rainier's here as well. I'll be here afterwards for any Q&A. We've got a couple of meetings coming up in about half an hour as well, so if you guys have any questions, we'd love to answer them. And that is the end of the presentation. Thank you very much. Appreciate it.